Well, welcome back to Maths Specialised. We're starting a new topic now, and it's for Criterion 6, and that is differential calculus and applications to areas and volumes. Now, the essential part for this particular topic is to make sure you have under your belt a good working knowledge and high skill level at differentiation. Okay, so just given what you've worked through already with maths methods, just being able to differentiate given your basic functions, whether it's a normal function, or whether it's a trig function, or whether it's a exponential, or whether it's a log to the base e function. So, and combinations of these, composites, where you've got to do the function of a function, okay, the chain rule, or the product rule, or the quotient rule, or a combination of all of those. Okay, you need to be fluent in the use of those. Okay, so given that, we're going to move on to the next part in this topic, or really the first part, and it's called implicit differentiation. Okay, so we're looking here then at our first set of examples. Now, implicit differentiation is what we use when the equations that we're working with are not written explicitly. Okay, it's implicit rather than explicit. And what we mean by that is an explicit equation has the variable y as the subject, so y equals 2x plus 3. Or y equals sine 3x. Okay, it's always y equals something. Okay, but some equations aren't easily written in that form. Okay, and so we need to look at ways of differentiating those equations, and in order to do that, we use a process called implicit differentiation. Okay, and in that case, every term in the equation is differentiated with respect to x, including the y terms. Okay. Now, if we just think about a simple function like y equals 3x, then what we're doing is we are essentially differentiating both sides with respect to x. Okay. The left-hand side, differentiating y with respect to x, simply becomes dy dx. Okay. And differentiating the right-hand side, as we know, becomes 3. So when we're saying that we differentiated the terms with y in them, this is what happens. Okay, the y becomes dy dx. And we'll look at other examples as well. In fact, this first one here, okay, we need to differentiate the equation y squared plus 3x squared equals 4. Clearly, in this particular example, we could rearrange it, okay, so to make y the subject and then differentiate explicitly. But we're just going to look at differentiating it implicitly. Alright, so this first example, we've got y squared plus 3x squared equals 4. Now, even this y squared term is a composite function. Okay, we've got y and it's squared. Now the derivative of y is dy dx. Okay, but we also have the fact that it's squared, so we need to go 2 times y when we differentiate the outside part. Okay, 2 times y, and multiply that by the inside part, which is y, becomes dy dx. Okay, so it's 2 times y, so we're really applying the chain rule here. Okay, 2 times y, and multiplying that by the derivative of y, which is dy dx. And then the next one is simple, it's simply 2 times 3 is 6x equals 0. Now, we don't just stop here. Okay, the question's saying differentiate the equation to find dy dx in terms of x. So first of all, we'll rearrange it so that we're making dy dx the subject. So 2y times dy dx equals negative 6x. Dy dx equals negative 3x over y. So we've got dy dx as a subject, but it's not entirely in terms of x because we still have this y here. So what we need to do is substitute y for the expression here. So we're going to rearrange this, make y the subject, substitute that in for y. So if we have a look, this is going to become y equals plus or minus the square root of 4 minus 3x squared. So this needs to then go in here. Plus or minus 4 square root of 4 minus 3x squared. Now, clearly when we've got the plus or minus here and we've already got a minus, it's still going to be plus or minus. You could be pedantic and change your plus or minus to be the other way around. It really makes little difference. Okay, 3x over square root of 4 minus 3x squared. Now we do have a condition here, and the condition is that whenever we have a denominator that has a variable in the bottom, there is often a situation where we need to ensure that we're not going to be dividing by 0. Okay, and so the condition is that we don't want 4 minus 3x squared to equal 0, which essentially is the same as saying we don't want 3x squared to be equal to 4. Which is essentially the same as saying we don't want the absolute value of x to be equal to 2 over root 3, or another way with a rational denominator, 2 root 3 over 3. Now that's for that to be 0, but I mean that's not really the only condition. We also don't want it to be less than that value, because when it's less than that value, this inside term here is going to be negative. Okay, and we're dealing with real numbers in this situation. Okay, so we don't want to be taking the square root of a negative number, because there's no real solution for that. So effectively, our condition is the absolute value of x must be less than 2 root 3 over 3. Okay, so that's important, just an important little consideration when you've got situations like this. Okay, you just need to look at what are the restrictions on our variable x. Okay, alright, so we're going to look then at the next problem, or a couple of problems here. Okay, example 2, and A, we've got 2xy squared equals x minus y. Now, we've got here a product, we have here a composite function, okay, with y squared, so we need to apply the chain rule here, but it's also a product rule, and we can differentiate these separately. So we need to consider this. Okay, so if we let that equal u and that equal v, then we've got u equal 2x, which makes u dash equal to 2. We've got v equals y squared, and so v dash equals 2y. We might make it y dash, okay, just to simplify things a little bit, okay, make it a bit easier and quicker to write. So y dash instead of dy dx. Okay then, so we need to apply the product rule. You remember is v u dash plus u v dash. And so v is y squared. So it's y squared times u dash, which is 2, plus u, which is 2x, times v dash, which is 2y times y dash. That's our left-hand side dealt with. Right-hand side then is going to be the derivative of x minus the derivative of y. So that's 1 minus y dash. Okay, let's look at collecting our like terms then. Okay, we can perhaps rearrange it and just simplify it a little bit first. So this is 2y squared plus 4xy y dash equals 1 minus y dash. Okay, so we're going to look at rearranging, because our question is saying find dy dx in terms of x and y. Okay, it doesn't have to be all in terms of x, which is good, it makes it a little bit easier. Okay, so we need to bring our dy dx term, our y dash, over to the left hand side and take our 2y squared over to the right hand side. So we have 4xy y dash plus y dash equals 1 minus 2y squared, and we need to take out factor here to make sure we get y dash by itself. So it's 4xy plus 1 in brackets outside of y dash equals 1 minus 2y squared, and then y dash equals 1 minus 2y squared over 4xy plus 1. Didn't really need those brackets. Okay, so that's our solution. Let's look at question B. We've got x squared y cubed minus 5 equals 4x. Again, we've got a product here, so uv, and when we work that out, okay, u dash is going to be 2x and v dash is going to be 3y squared times y dash. Okay, so on the left hand side, when we differentiate, we're going to apply our product rule, vu dash plus uv dash. So then v is y cubed, timesing that by u dash, which is 2x, and plus uv dash, u being x squared, times v dash, which is 3y squared times y dash. Then the derivative of -5, which is 0, so we'll leave that, and that's equal to the derivative on the right hand side, which is 4. Okay, just to simplify this, 2x y cubed plus 3x squared y squared times y dash equals 4. And we're going to rearrange now. We want to make y dash the subject, so we've got 3x squared y squared times y dash equals 4 minus 2x y cubed, and then y dash, or to y dx, is equal to 4 minus 2x y cubed all over 3x squared y squared. Okay, so that one's complete. Differentiated and written in terms of x and y. Okay, so we'll leave that at that stage. We've got more examples to go through. We'll look at that in the next video.